Retaining walls. Figure 1 shows an example of a retaining wall under construction. Definition. What is a retaining wall? A retaining wall is any constructed wall that holds back soil, a liquid, or other material where there is an abrupt change in elevation. Cantilevered retaining walls are the most common type and are commonly masonry or concrete in construction. In this section, we will be dealing with concrete cantilever retaining wall. However, many of the principles covered are transferable. Retaining walls are found across a wide variety of contexts, from basement to highways and rail to ports, and can vary in their design to suit the context. So in this section, we will be covering cantilevered retaining wall, the types of cantilevered retaining walls, and the EuroCode 7 design philosophy. Cantilever wall. This wall has a vertical or inclined stem monolithic with the basement slab and is suitable for heights of up to 7 meters. Typical dimensions for the wall are given in figure 2. So, cantilever retaining wall should be less or equal to 7 meters. Its slenderness is possible as the tensile stress within its stem and base are resisted by steel reinforcement. If the face of the wall is to be exposed, then general practice is to provide it with a small backward batter of about 1:50 in order to compensate for any slight forward tilting of the wall. So you can see figure 2, which shows typical dimensions for cantilever retaining wall, and there are two types of cantilever retaining wall, that is the cantilever wall and the counterfort wall, as you can see. So a retaining wall is subjected to both shear and bending stresses. In the stem and base caused by the lateral pressure induced from the soil that it is supporting. A mass construction gravity wall can take such stresses in its stride, but this is not so for the vertical stem of a reinforced concrete retaining wall. If structural failure of the stem is to be avoided, then it must be provided with enough steel reinforcement to resist bending moment and to have a sufficient thickness to withstand the shear stresses through the section to its height. It is in this situation that a limitation on the practical height of the wall stem of 7 meters is imposed for a conventional retaining wall. As the dimensions of a wall increases, it becomes less flexible and the lateral pressure exerted on it by the soil tend to be higher than the active value assumed in the design. Counterfort cantilevered retaining wall, that is in figure 2, incorporate wing walls projected from the heel to the stem. The stem between counterfort wing walls is thinner and spans horizontally between the counterfort wall. The counterfort act as a cantilevered element and are structurally efficient because the counterfort are tampered down to a wider or deeper bays where moments are higher. However, the high cost and increased complexity of forming the counterfort and infill stem walls make such wall less practical and desirable unless the situational complexity requires it. You can see why counterfort cantilevered retaining wall are not often all common, because they have increased complexity, and also there is a high cost, so it is best to avoid it when the situational complexity does not require it. Types, typical terminology. Backfill. Backfill is the soil placed behind the wall. Butter. Butter is the slope of the face of the stem from the vertical plane, usually on the inside earth face. Foundation or footing is that part of the structure below the stem that supports and transmits vertical and horizontal forces into the soil below. Toe. That portion of the footing which extends in front of the front face of the stem or away from the retained earth or water or anything that is being retained. So the toe is away from the retained material. Heel. That portion of the footing extending behind the wall or under the soil. Retained height. The height of the earth to be retained generally measures upward from the top of the footing. Stem. The vertical wall cantilevering above the foundation. Surcharge. Any load placed in or on top of the retained soil, either in front or behind the wall. So surcharge is any load placed in or on top of the retained soil. EuroCode design philosophy. The design philosophy adopted in EuroCode 7 is the same as that adopted in all the EuroCode and advocates the use of limit state to design that the serviceability limit state are not exceeded. Serviceability limit states are those states that, if exceeded, rendered the structure unsafe, even though no collapse situation is reached, such as excessive deflection, settlement, or rotation. In contrast, the traditional method of the use of lumped factor of safety, the standard promotes the use of partial factor of safety and thus reflects a significant shift from the previous UK geotechnical design practice, where once the design method treated material property and loads in an unmodified state and applied a factor of safety at the end of the design process to allow for the uncertainty in the unmodified value. EuroCode 7 guides the designer or the engineer or the structural engineer to modify each parameter early in the design by use of partial factor of safety. This approach sees the representative or characteristics value of the parameter, for example, load, soil strength parameter, converted to design value by combining it with a particular partial factor of safety for that parameter. The states that the limit state should be verified by one of four means: by 1. Calculations, 2. Prescriptive measures, 3. Experimental models and load tests, 4. An observational method. In this lesson, we shall only consider geotechnical design by calculations. So the standard states, the EuroCode 7 states that the limit state should be verified by four means: calculation, prescriptive measures, experimental model, and observational methods. Now, to facilitate an appropriate design, projects are considered as falling into one of three geotechnical categories based on the complexity of the geotechnical design together with the associated risks. Category 1 is for small projects with negligible risks. Category 2 is for conventional structures, e.g., foundations, retaining walls, embankments. And category 3 is for structures not covered by categories 1 and 2. It is obvious that most routine geotechnical design work will fall into geotechnical category 2. To enable the limit states to be checked, the design values of the geotechnical parameter, that is the ground resistance, and the actions, e.g., forces or loads, must be determined. The design values of actions are derived by multiplying the representative values by appropriate partial factor of safety. The design values of geotechnical parameter are derived by dividing the characteristic value by the appropriate partial factor of safety. The resistance is derived from the design value of actions and ground parameter. The design resistance can either be taken as equal to a reduced value, of which is derived by dividing by an additional partial factor of safety. The choice of which partial factor of safety to use is governed by the nature of the action and by the design approach being used. Actions are classified as permanent, that is G, either favorable or unfavorable, variable Q, accidental A, or seismic AE. The effects of actions are also considered in the design.